we talked about sections 1, 2, and 3, and I asked you guys to work on homework 1 through 12. That homework is obviously not due today, but if you have questions about anything, we can certainly address that while we're here. Does anybody have a question about this 1 through 12? Sydney.
Can you do number 12?
Sure. Again, just while I'm sorting this out here real quick, the homework is due Sunday at midnight. The way you do your homework is you'll either do it directly in your homework tab of OneNote, or you can do it on paper, take a picture, and drop that file into the homework tab of your OneNote. Either is fine. Just make sure you're naming your homework assignment, labeling it in a way that's easy for me to understand what it is that I'm looking at. So 12 here. Okay. So it asks for the range. If I'm going to answer this algebraically before I can do the range, I need the domain. So I'm going to start there. The implied domain here is obviously all real numbers, since there's no context to this problem. It's just variables that don't represent anything in particular. For the relevant domain, the operations I see going on are addition, subtraction, and square roots. Of those, the square root is the only one that I need to worry about. So I'm going to take everything underneath the square root and say that has to be non-negative. So to solve that inequality, we add 3 to both sides. So my domain is that. Okay there? Okay. Next thing I'm going to do is I'm going to check to see if this function is increasing or decreasing. I should be able to look at the form of this and go, okay, that's just going to be like a square root function with a positive coefficient, so it's increasing. If you weren't able to do that, that's okay. Just type in your calculator and look at the picture. It's easy to tell if it's increasing or not. So since that's increasing, I know the lower bound for the range is going to equal h of the lower bound for the domain, and the upper bound for the range is h of the upper bound for the domain. So the lower bound for my domain was 3, so h of 3. So square root 3 minus 3 plus 2, which is 2. And because the domain that I used had a bracket on it to get the lower bound for the range, I know the lower bound for the range also has a bracket on it. So because this 3 had a bracket attached to it, the 2 that I get also is going to have a bracket attached to it. Sydney, so far so good? Okay. So the h of the upper bound is h of positive infinity. So that's square root of infinity minus 3 plus 2. So infinity minus 3, still infinity. Square root of infinity, still infinity. Plus 2, still infinity. So I know I'm going to get an infinity here. And because this is an upper bound, I know the type of infinity that I have is positive. And those positive, all infinities always get a parenthesis, so I'd be done. Maddie?
For the upper and lower bound, how do you determine which one is like which is going to be upper or lower again?
By whether the function is increasing or decreasing.
Okay.
If it's increasing, they're the same. Upper goes to upper, lower goes to lower. If it's decreasing, they switch.
And then it has to do with negative, right?
It has to do with whether the function is like increasing, like getting bigger, or decreasing, getting smaller. Sydney, is that?
I have a question on that.
Okay. Anybody with a follow-up on this before we move on to a different question? Ariana?
Oh, sorry, why does the 2 have a bracket?
Okay, so the bracket and parenthesis in the range is tied to the bracket and parenthesis from the domain. Since we used the 3 to get the 2, I look at the bracket or parenthesis on the 3. It's a bracket, so I get the same sign or the same symbol with the 2. Is that good? Okay. Who's next? I saw another. I keep wanting to say Joe, but you're not Joe. You are Luke. 10? Sure. So 10 here we have h of x equals x minus 1 over the square root of x. So again, we're looking for domains here. So the implied domain is obviously all real numbers because there's no context to this problem. The x's are just x's. They don't represent anything else. So the relevant domain, I'm going to look at the operations involved. I see subtraction. Doesn't matter. I see division. So I know that the denominator cannot equal 0. And I see a square root. So I know the stuff under the square root has to be non-negative. So if I look first at the square root of x cannot equal 0, I can square both sides and I get that x cannot equal 0. And x is greater than or equal to 0. There's nothing to do with that, so I can just keep it the same. Now here, you could turn that not equal to into an inequality, but I think there's an easier thing to do here. If you think about, okay, what is both not equal to 0 and greater than or equal to 0? Well, that's just equivalent to x is greater than 0, right? So I'm going to do that rather than treating as two separate, like a bunch of separate inequalities. I'm just going to do this and just really simplify things down. Since x can't be 0, and x has to be greater than or equal to 0, well, it just has to just be greater than 0, right? So from here, it's now just going to be that. And that little observation there can save you a lot of screwing around with a lot of different intervals and trying to merge those things together. It becomes a big hassle. In general, if you have a situation like this where you have like fraction, square root of stuff, you can just say the stuff has to be greater than 0 instead of greater than or equal to 0, and then separate the square root of the stuff not equal to 0. You can just simplify it all down to just that stuff now has to be strictly positive. You lose the 0 because it's in the denominator rather than the numerator. Does that feel okay, Luke? Luke. Okay. Others? Anybody else that wants to go at one of these? Anthony? 8? Sure. So we have, what is that? K of x. Oops, that's a pretty bad x. Equals x over x squared minus 1. So again, the implied domain is all real numbers. The relevant domain, then, I have to look at the operations. I see division, I see squaring, I see subtraction. The only one that matters is the division, right? So I know that that denominator has to be non-zero. So to solve this, what I have is a quadratic equation, right? So I can solve the quadratic equation with the quadratic formula. I could factor it. I could solve this directly. Kind of any of those are fine. Anthony, do you have a preference? Okay, well, let's factor this. That's probably the most natural for most of us. So you notice that that's a difference of 2 squares, so x plus 1, x minus 1. I can apply the zero product property. And I get that x cannot equal 1 and x cannot equal -1. And now I could try to turn that stuff all into inequalities and then try to combine the inequalities. But I think that makes more sense here to just use a little bit of common sense. So what we have here is everything that's less than -1, or the stuff between -1 and +1, or the stuff that's greater than 1. Right? If it can't be -1 and it can't be 1, there's 3 spots. There's stuff less than -1, the stuff in between the two, and the stuff bigger than 1. Is that okay? And it's probably easier to do it to just use a little bit of common sense and think about it, than try to resolve each of these guys into separate inequalities, and then you have like overlapping inequalities that kind of need to be combined, and it's just like becomes way harder than it needs to be if you know, versus just kind of applying a little bit of common sense there. Now, once I've gotten to here, I can just write 3 intervals because I have 3 inequalities. So less than -1 is -infinity to -1. Between -1 and +1 is just -1 to 1. And greater than 1 is 1 to +infinity. And everything gets a parenthesis because we have strict inequalities throughout. But that's probably the easiest way to kind of look at that one. Does that, Anthony, was that okay? And again, most of these problems, like once you've gotten it, you know, like once you've done the relevant domain part and solved those pieces, to get the interval or to resolve it into inequalities, sometimes it's just easier to think about like, what is it that I really have here? You know, like this one was definitely one where if you try to write like, okay, x could be less than 1 or greater than, or less than 1 and greater than 1, or it can be this and this and this, and then you have to like try to piece those things together because some of that stuff overlaps and some of it doesn't. It's just like, it gets really confusing. But if you just pause for a minute and be like, okay, it can't be this or this, so it's this or this or this. Now, to think of that the first time seeing it maybe is not obvious. But after working through an example and seeing it and going, oh, yeah, that does make life a lot easier, then hopefully you remember that kind of a trick. Don't let common sense get in the way of, you know, don't let what you're shown, like the example you're shown in class, get in the way of common sense, is the takeaway there. Sometimes it just, you know, there might be a simpler way to do it that is special to this case that doesn't fit the general way that we kind of did things in class. You know what I mean? Oftentimes I'm going to give you a method that works all the time that might be harder than a special case that works in a particular time. Don't be afraid if you see a particular time shortcut to use that, like I kind of did here. Okay. We good? All right. Let's get after it today. So we'll do 2 sections again today. We're going to talk about section 1.4 and 1.5. Section 1.4 is about increasing and decreasing functions. So increasing and decreasing is like a characteristic of functions. It's like an adjective you can use to kind of describe a function in itself, in its entirety, or even just like a part of it. So let's start with our technical definitions. So we say a function f is increasing on a given interval if for any 2 points on that interval a positive change in x. Oops. Positive change in x results in a positive change in y. Or I guess I should say f of x. It doesn't really matter that much. Now we'll explain kind of what this definition means and how to use it in a moment, because reading that, it's probably not entirely clear what it's saying. It's a little wordy. There's a lot of notation going on. It's a fairly simple idea, though, as we've already kind of made the assumption that we can look at a graph and tell if something's increasing and decreasing to do the ranges. So we've already kind of talked about this. The definition for decreasing, we change one word. Instead of being a positive change in f of x, we have a negative change in f of x. Rather than rewriting that entire definition, I'm just going to do that and write the different word there. And there's one other type of interval. It's a constant interval. And here, instead of a positive change in f of x, it's going to be a no change in f of x. So rather than recopying that definition that's virtually the same 3 times, I just wrote the, if it's a decreasing, it's the same definition, but instead of positive, we say negative. You guys get what I mean by what I'm doing with the, just to not have to write it 3 times. That's okay? Okay. So let's explain a little bit what this means now, okay? Because again, like reading the definition, it's like, that is some wordy crap right there. And it is. The nice part about this is that there's an easy visual interpretation of what we're really saying here. And really that's the interpretation that we need to like do the problems in the homework. We're not like proving that things are increasing and decreasing, so we don't really need the precise definition. Just like a visual interpretation would be good enough. So let's just say we have this example. So here's our function. If I think about a little person that walks along my function from left to right. So there's my little person. This first section of the graph is all uphill, right? If that little person is walking uphill, the function is increasing. The technical definition says that if you take 2 points on that interval and you subtract the coordinates so that the difference in x's is positive, so you're picking the point to the right and subtracting the x from the coordinate from the point on the left, if you also do the same thing for the y coordinates, that should be a positive number, because if you walk from left to right and it's increasing, the point on the left is lower than the point on the right. That's all it's really saying. Sydney?
Would that be decreasing?
So it's left to right,
But the arrow is pointing.
but we're walking left to right.
Okay.
That part has to be that way. You can't, it's like reading a book. If you read a book, you read from left to right in English. There's other languages, I guess, that I think read the opposite way. But in English and in mathematics, we're always reading a graph from left to right. So when we talk about things increasing or decreasing, we're talking about going from left to right. Because if we don't say that, then like if I read from right to left, everything is reversed. You know what I mean? So it doesn't matter that its end behavior is negative. That's not what we're talking about right now. That'll come later when we talk about end behaviors, which I think is where you're at. But it's always reading from left to right. And that's the key, is making sure that we're thinking about everything from left to right, like we're reading a book. The next section, our little man is in the middle here. That section is flat. So that section would be constant. And in the last section, our little man is now going downhill. That section is decreasing. Sydney, the other way you can think about it is if like that part of the graph has a positive slope, it's increasing. But we don't like to say slope because that slope is really only defined for straight lines. And if it was like a curved line going up, it still is increasing even though it technically doesn't have any slope there. But like it's the same idea, if that helps. Kind of remember that is link it to another idea that we're already familiar with. And it's like, it's not technically slope, but like you get what I mean by positive slope. We'll say positive slope-ish. All right, so let's assign some coordinates to these couple of points here so that we can do this as an example. So let's say this first point is maybe -1, 2, and this point is maybe 3, 2. Those seem like reasonable approximate coordinates. You guys buy that? All right, so our first section of the graph here is increasing, right? When we describe these intervals of increasing, decreasing, and constant, we're always describing the location on the graph. When you describe the location of a function, you're always using the x-coordinate to describe it because that's the independent variable. So our increasing function begins here with the left arrow. That left arrow represents -infinity. And I'll put the parenthesis in right up now, since we know all infinities get a parenthesis. And it ends here at the point -1, 2. Again, I don't care about the y-coordinate when I'm doing these intervals, only the x. So this ends at -1. Now, why did I use a parenthesis here? If I look at the definition, we describe an interval, the parts of an interval as increasing if you can pick a point to the right and we have a positive slope, or a positive rate of change, I guess I should say. If I pick a point to the right of -1, 2, I don't get something with a positive rate of change, right? So -1, 2 can't be included as a positive interval. In general, the bounds of all of these intervals, increasing, decreasing, constant, all get parentheses all the time. You don't have to think that hard about it. I just wanted to explain why I'm using a parenthesis here. And that follows for all the bounds for all these intervals always. Okay? Domains and ranges can have brackets. Increasing, decreasing, constant, nope. Okay? And that's nice, right? Like we love it when the math has a rule that's like, it's always do this. The next one is constant. So our constant interval starts at this point, -1, 2, but all I care about is its x-coordinate. So it starts at -1, and it goes to this point, 3, 2, but all I care about is x-coordinate. So we end at 3. And then lastly, our decreasing section starts here at 3, 2, but all I care about is its x-coordinate, and ends with the arrow to the right. The arrow to the right is positive infinity. And again, if you struggle with the arrows, you can think of this one like this is pointing to the left and down. So if it helps, like write in the coordinate as like to the right is positive infinity and down is negative infinity. If that helps, do that. You can do that right at the beginning so you don't like goof up the infinity sign because you're like see a down arrow and write negative infinity. Everybody's okay? Pretty easy. Let's look at a slightly more challenging example here. For this slightly more challenging example, I'm going to generate the graph digitally so that it's a little bit more clear. This would be the other advantage of doing it this way is that it'll look the same as if I was to do something similar on the test and give you a graph and ask you to do this for it. So it'll look the same way as like a test question might, so you can get used to what that it would look like. Because I'm not going to hand draw a graph and put it on a test, because it's like, I can't be that neat. You know what I mean? Those of you with the bad penmanship feel my pain. So here's our graph. Oops, actually I want to do one thing to this first. Let's do that. Okay. There we go. I just wanted to zoom it out a little bit more. All right. First thing to say when interpreting something like this. Anywhere where the graph is leaving the viewing window, you can assume there's an arrow on it and it's continuing kind of in that same direction forever. So you can put like an arrow here and here and here and here and here and here. Those of you in the back, those vertical lines are dotted. Those are asymptotes. Maybe it's not, I tried to zoom it a little bit so it'd be easy to see that, but on a piece of paper it would be all the way in the back with a zoom that I can see the whole thing. Maybe not, but those vertical lines are asymptotes, in case you couldn't see that. So take a look at the graph. How many places is this graph increasing? Or how many sections of the graph are increasing? Should see 2, right? So if we look at this section, we're going uphill the whole time till we hit that asymptote. And then after the asymptote, we're going all the way uphill till we get to 0. How many decreasing sections do we see? 2 as well. Starting at 0, we go downhill till we get to the asymptote. And immediately following the asymptote, we go downhill the rest of the way. Notice that there's no place where we're constant. We're not constant at 0 because an interval needs to be more than 1 point. Even though the graph is, you could say the graph is flat at 0. Okay, so let's write our intervals then of increasing and decreasing. So we start here at this left arrow. So we'll start with negative infinity. And we end at the asymptote, which appears to be about negative 3. We then pick up at the asymptote, which is negative 3. And we stop increasing when we get to 0. Everybody good there? For the decreasing, we start at 0 and we end at the asymptote, which appears to be 3. And then we start at the other side of the asymptote at 3, and we go on to the right forever, so 3 to positive infinity. Feel good? Great. The next topic here, related in a way to these intervals of increasing and decreasing, is extrema. So extrema are points on our graph, and they're really kind of like the relative high or low points on the graph. So there's really 2 types of extrema. You have maximums, or maxima, that's the plural for maximum, and minima, that's the plural for minimum. So we say that a maximum, actually I'm going to do it this way. I'm going to do the same thing. And we'll just color code my definition because most of the words are identical. So I'll do the maximum first, and then I'll write above it in red the words that change for the minimum. Maximum of a function f is a value f of c that is greater than or equal to all other range values of f on some interval containing c. So for minimum, it's less than or equal to. That's the only change. Okay. Next up, we would say that there are two types of maximums and two types of minimums. There are absolute or global maxes and mins. So this would be the overall highest or lowest point. Well, we should say points, plural, because you could have like a tie for highest and then have multiple global maximums, or a tie for the lowest point and have multiple global minimums. And then you have local. So here you just are the highest or lowest point in some neighborhood. So if you have a infinite continuous function, like most of the things we deal with, what we're talking about for the locals are any hill top is a local max, and any valley bottom is a local min. Everybody's okay with that? And most of the stuff we'll deal with are continuous and infinite. If it's not infinite, you might have a local min or max at like the start or end of a segment, right? That's not necessarily a hilltop or a valley bottom. Or if it's discontinuous, you might have a situation where like, no, I don't think you can get anything weird if it's this. You might be able to. I'd have to think harder about it. But it's too hard to where it would be within the scope of this class. Maybe if you had a removable, if you had something removable, like just an open, like something like that where you just don't have the maximum then. But like I wouldn't do that to you guys. That's way beyond the scope of this. Paulie, what's up? Oh, keep on stretching then, brother. All right. So let's look at an example. One of the things that we'll want to, or that I'll want you guys to be able to do, is if I give you a function, is to actually find the coordinates for these, and label what they are, whether they're global or local maxes and mins. To actually do this by hand is a calculus problem and well beyond the scope of this class, and not even really an easy calculus problem. It's actually quite challenging of a calculus problem. But we can use our calculator to do this. And the calculator handles this quite nicely. Now, keep in mind the calculator is not finding the exact value of these points necessarily. It has like an approximation algorithm that'll give you like, the right answer up to like 10 decimal places or something, which for our purposes is plenty good. But just to let you know, the calculator's not doing any calculus. It can't. But it can do like an approximation process, which is totally different than what you'd be doing in a calculus class, but easier for a machine to execute. Okay, so to turn on your calculator, press the on button in the lower left-hand button, or lower left-hand corner. To find these maximums and minimums, your calculator is going to need a graph. To graph something on your calculator, you have to press the y equals button in the upper left-hand corner. My first order of business would be to clear out my y equals menu. So if I have anything in these equations, I'm going to clear them out of there. I'm also going to scroll down to the very bottom because my calculator's been rattling around my backpack, maybe without a case on, for a while now, and I might possibly have some gobbledygook down at the bottom that I need to get rid of that might cause a problem. Once I've cleared out all my y equals slots, I'm going to go back and check to make sure that at the top where it says plot 1, plot 2, plot 3, none of those should be highlighted. So if your calculator looks like this, where one of the plots is highlighted, move your arrow or move your cursor with the up and down arrows up there and just press enter to unhighlight that plot. That can cause big problems when graphing. Whenever we're graphing, unless I tell you otherwise, those plots should not be on. Next thing I'm going to do is type in my function exactly as it looks on my sheet of paper. The X button is right next to the green alpha button. The exponent button is right above the division symbol. You have to make sure you remember to press the right arrow to exit out of the exponent. At least if you have a calculator you bought within like the last, 5 years or so. Some of us might have something with an old operating system where they don't make you do that. I preferred it that way. But you had to use a lot of parentheses if you had many things in your exponent, which could be kind of a pain, but in high school class, I think I definitely pressed the right arrow more than I would have to use a parenthesis. So I think it's a decrease in functionality. Once I have everything typed into my calculator as appears on my sheet of paper, I can ask the calculator to graph this. To get a good picture, I need to pick an appropriate window on my calculator. Last time I used my calculator is God knows when. I have no idea what my window currently is. In those sort of situations, what I'm going to typically want to do is press zoom and then pick standard. That's option 6. That'll give you the normal -10 to +10 on the X and then -10 to +10 on the Y viewing window, which more often than not is going to give us an appropriate picture. And I think I screwed up what I typed into my calculator. Oh my goodness gracious, look at that. I need a plus sign there. Good thing I've done this now 6 times, so I knew immediately when I looked at it, it's like, that's not what I'm supposed to have. Okay. So if I look at my picture here, it looks like I have a global minimum right here. That's the lowest overall point. Everybody agree? I have a local maximum here. It's local because there's still points that are higher than that one. I have a local minimum here. Again, we have points lower than that one. And there is no global maximum because I have arrows pointing up on the graph. So any point you name, we can find one higher than that one. I'm just going to record that information now. So I have a global min, I have a local max, I have a local min, and then I have no global max. I like to record them from left to right on my screen because when I find them, I'm going to find them from left to right on my calculator because it makes everything easier if I do it in that order. Is it not required? It is not. But like, why would you do it the hard way when you can do it the easier way, right? It's less buttons to press. Everybody good? Okay, the menu that I need to access to find these maximum minimums on my calculator, I get to by pressing second. That's the blue button. And the trace button, which is on the top row of buttons on my calculator. If I look through that list, I see 2 commands that should be obviously the 2 that I'll be using. They are minimum and maximum. The first point I'm looking for is my global minimum, so I'm going to pick the minimum command. When I press enter, the calculator now is going to ask me 3 questions. It's going to ask me for a left bound. So what it needs is some point on the left-hand side of my minimum that I'm looking for. My global minimum is here. On the left side of that minimum is something on this part of the graph. So I'm going to move my cursor using the left and right arrows. See my cursor right here? Until it's over there somewhere. It doesn't really matter where it's at. That looks good. And then I'll press enter. The question is now changed to a right bound. So I need to move it somewhere right of that minimum. So I want it somewhere like over here on the graph. So again, I'll use my left and right arrows to move my cursor over there. That looks good. Doesn't really matter where it's at over there, just has to be somewhere over there. I'll press enter, then asks for a guess. As long as I have only one extrema inside the interval that my left and right bound that I picked, doesn't matter what your guess is, just press enter. Gives me the x and y for that global minimum. I'm going to take that and round it to 3 decimal places because who wants to write down that many numbers? Not me. Again, you guys should all have exactly the same answer that I have here. I would suspect it's possible that if you have a slightly newer operating system or a slightly older operating system, maybe the rounding that's programmed into the algorithm that it's using to do this is a little bit different. So maybe the last digit is different, but I would be even surprised at that, Sydney.
So you want us to have 3 decimals?
That's what I'm just choosing to round this problem to.
Sure.
The directions would tell you what the rounding would be. But in general, 3 is probably sufficient. Just enough to to let me know that you couldn't have guesstimated it, right? That you actually had to know how to do the calculator process to get that degree of accuracy. Next up is my local max. So second trace. This time I'll choose the maximum command. Left bound, so I'm going to move my cursor somewhere over here. Press enter. Right bound is it's got to go somewhere over here in that little section there. So that looks good to me. Press enter. I guess anywhere in there is good. There's my local max. We doing okay, peeps? Okay, why don't you guys try to do the local min by yourself? I'll do it alongside. When I get done, you'll be able to still see the point, so you know if you did it correctly. But I'm just going to hammer that out real quick. How'd we do? Good. Again, something you probably did last year in Algebra 2 class. I know that my students did it at one point, but it's been a little while since you did it. So if you forgot how to do this on your calculator, that's not a big deal. If you didn't have your calculator with you today, you can always go back and look at the video. This part occurred around the, 35 to 40 minute mark is probably the beginning of the calculator piece. So you could fast forward to there or whatever. Okay. So we have this list of extrema, these mins and maxes. Imagine if you had just this list of extrema and told that you had an infinite continuous function. With just that information, we could also write the intervals of increasing and decreasing. We wouldn't need the actual graph. We wouldn't need the actual function. If I just have the extrema and I know that it's continuous and infinite, I can do this. So what I'll do is I'll look at my list of extrema, and actually I don't even need that. I'll look at my list of extrema and figure out which point comes first. Easy to do that because it's just looking at the one with the smallest x coordinate. So the first point is my global maximum. So to go down to a maximum, my graph would have to look like this, right? That's decreasing. So I go -infinity to the x coordinate on my global minimum. Next, I go to my local maximum. So that has to turn up to my local maximum. That part is increasing. So I go from the x-coordinate of my global minimum to the x-coordinate of my local maximum. From there, I go to a local minimum. So I go decreasing again. So I go from the x-coordinate of my local max to the x-coordinate of my local min. And then from there, that's the last thing, so it just must continue on up to complete the valley for that local minimum. So we'll start at that local minimum and proceed for positive infinity. Yes, sir?
So for the decreasing, shouldn't that be the last number? Shouldn't that be negative 3.030?
So we're always describing the x-coordinate, right? None of these are points. They're not x's and y's. They're an interval. So they're from this x to that x. So the takeaway here is the x-coordinates from my extrema are the bounds for my intervals. You're welcome. As long as our function is continuous and infinite, that'll always be the case, that the extrema, the x-coordinates for our extrema are the bounds for each of my intervals of increasing and decreasing, along with the infinities, obviously. Sound good? That closes that section. The next section is all about symmetry. Again, symmetry is another descriptor of a function, so that's a type of property the function may or may not have, just like increasing and decreasing. Some functions are all just increasing, or might all be decreasing, or might have some parts that are both. Symmetry is an all or nothing one. So we're going to talk about three types of symmetry. There are three major types that we'll talk about. There's lots of different types of symmetry, but there's only three that we care about for this class. The rest of them I would consider beyond the scope of what we're interested in. The first type is symmetry with respect to the x-axis. That phrase, with respect to, is one that comes up frequently in mathematics. I abbreviate that as WRT. You can do that if you want, or you can write out with respect to. But it's common enough that I don't mind using it. Yes, Sydney? Of course. So let's look at an example of what we mean by a graph or a function that's I shouldn't say a function. Let's just say a graph that has symmetry with respect to the x-axis. So this is an example of a graph that's symmetric to the x-axis. Basically what we're saying is if I take the half that's above the x-axis and I reflect it across the x-axis, it's going to lie exactly on top of the part that was below the x-axis. So basically what we're saying is that if I have the point AB, I also have to have the point A negative B. Is that okay with everybody? Notice this is not a function here. Right? You can't be a function, be symmetric about the x-axis. At least a function of, y in terms of x. So in general then, if I have a point A, means that if I have the point AB, implies that I also have to have the point A negative B. What that says is that f of x has to equal negative f of x. Right? So that f of A gives me B, and it also gives me negative B. Okay. We're much less interested in that type of symmetry because you can't be a function and have that type of symmetry. The next one is symmetry with respect to the y-axis. We'll use the term even to describe functions that have this sort of symmetry. So if you're a function that's symmetric to the y-axis, we call those even functions. That's a term that maybe you remember from your Algebra 2 class. I think in my class we talked about this. I don't know what Miss Morgan did. She might not have mentioned it. That's okay. So what we're saying then, if we're symmetric about the y-axis, if I take the stuff on the right-hand side of the y-axis and reflect it across the y-axis, it should lie absolutely on top of the left side of the y-axis. So basically what we're saying is if I have some point AB, I also have to have some point negative AB. Or more generally, that f of negative x has to equal f of x. Right? F of a is b, and f of negative a also b. They're equal. Cool with that? The third type of symmetry is 180-degree point symmetry with respect to the origin. I'm going to abbreviate point as PT. So what this graph looks like is something like this. Let's see if I can draw it good. So basically what we're saying is imagine we have some point here, and like I tie a rope to that point and a rope to the origin, and then I spin that rope 180 degrees. That point should also lie on the other part of the graph. Essentially what you're doing is you're reflecting twice, once across the x and once across the y, or in the other opposite order, it doesn't matter. So in general, what we're saying is if I have the point AB, I also have the point A negative B, or really that f of x equals negative f of x. I'm sorry, f of negative x equals negative f of x. So f of negative a is negative b, f of a is b, and then I make it negative. I have negative b. So these definitions are what we're going to be using primarily to do the homework here. So we'll be using these to do some proofs. So we're going to prove whether the function is odd, even, or neither. And the nice part is when we say proof, this isn't like a two-column geometry proof. This is just like an algebraic proof. And my tool for this are these relationships that we just established. So that's going to be my tool. Yes, sir?
So for 180-degree point symmetry, will that always be a function as well?
Could be a function as well. Doesn't have to be, because you could have like, like something like that fails a vertical line test, but is like still has that symmetry.
Okay.
And the same thing with the y, right? Like you could have something that is like two parabolas, one right side up and one upside down, that has that symmetry, but like isn't a function. But in general, yes, things that are functions can have that symmetry. If you have that symmetry, it doesn't necessarily make you a function. Cool? Good. Okay, so how do we start with this proof? Well, in each of the definitions here that we have for odd and even, for odd and even, we need to compute f of negative x and see what we get. Everybody see that? So that's what we'll start with. So we'll do f of negative x. When I have function notation, the thing that's inside the parentheses is what I'll input for x. So that means I'll have negative x to the fourth. If I take a negative and raise it to the fourth power, what do I get? Positive. So this negative x to the fourth becomes just x to the fourth plus 1. Notice that this is exactly f of x. So what we've shown here is that f of negative x is equal to f of x, which is our definition for even. So we're done. Is that okay? Okay. Let's do another. So we'll call this one g of x, just so everything's different. Okay. So this one, again, start the same way, right? Whether it's odd or even, start by doing f of negative x. In this case, well, it's really g of negative x. So that means I plug negative x in for my x's. Everybody okay there? A negative to the third power is still negative. So that 2 times negative x to the third just becomes negative 2x to the third. And positive 3 times negative x is just negative 3x. If I compare that to g of x, I notice it's not the same. The signs are not in the right, not correct. However, if I factor a negative sign out, what's left then is correct, or is f of or g of x, right? So like this part is g of x, and since I have a negative sign in front of it, I have negative g of x, and that is equal to g of negative x, so we know we're odd. Yes, sir?
Is it called even and odd? Because if the exponent's odd, then it will be negative, and if the exponent's even, then it will be positive.
Ooh, almost. Almost. What's the issue with that? Well, if you look at the first one, 1 has an exponent of 1, right? That's odd.
Okay.
The second, or part B, the exponents are 3 and 1. That seems to hold. But let's look at this example. You're very close, though. So let's say we have h of x is 4x squared minus 3x plus 9. Again, we'll start the same way. Looking at h of negative x, and then plugging the negatives x's in. 4x times negative x squared is just 4x squared. And then negative 3 times negative x is positive 3x. If I compare this to h of x, that's not the same, right? One of the signs is incorrect. Okay, well, if I try factoring a negative sign out, and look at that, and compare it to h of x, that's also not h of x. So here we've shown it's not even. Here we've shown it's not odd. So the only option left is neither. So my question for you, Dominic, here we had an even exponent, an odd exponent, another odd exponent, and it was neither. The first one, we had even exponent, odd exponent, and it was even still. So you're close though. Okay? Let's draw this back and let me give you a little bit more direction. I think you can get it. So if I look at these three functions, f of x, g of x, and h of x, what type of function are each of these? Well, they're not all quadratic because some of them have an x cubed and x fourth. What's more general than quadratic? With a P? Polynomial, right? They're all polynomials. What term or descriptor is related to the exponent of the polynomial but isn't the same as exponent in a polynomial? It's possible that you've conflated these two things into being the same. They are distinctly a little bit different. Anybody remember? It's related to the exponent and applies to polynomials. How about the degree? Remember, the degree of the polynomial is the sum of the exponents on the variables for each term would be the degree of each term, and then the biggest degree of terms is the degree for the polynomial, right? So the big takeaway, or the thing that we need to remember, is that for a constant, what is the degree for a constant? It's not 1, it's 0. Remember, because you can always think of these as having like an x to the 0 tacked on to the end, because anything to the 0 power is still 1. So like 1 times 1 is still 1, 9 times 1 is still 9. Ariane.
So are the even ones, are they always going to be symmetry with respect to the line?
Yeah, so the takeaway here, it seems like if I have all even degree monomials, that's going to be an even function. And if I have all odd degree monomials, it'll be an odd function. And if I have a mix of odds and evens, it'll be neither. That's the takeaway, right? And that is correct. Now, can we be a little bit more general than that? What if instead of saying we have the sum of even monomials is an even function and the sum of odd monomials is an odd function? What if we be even more general? What if we ask the question, the sum of even functions is even, or is an even function, I should say. Do we think that is true? It seems like it, at least if the even functions we're talking about are monomial functions, or even degree that certainly appears to be true. It seems like we have the evidence for that. What if we extend that, though, and just talk about an even function in general that's maybe not necessarily a monomial? Well, I don't know. Let's try to prove it. Should be something that's relatively easy to prove. So let's say f of x is equal to f1 of x plus f2 of x, yada, 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 plus fn of x, where f1 of x, f2 of x, all the way to fn of x are even functions. So that's kind of our setup here. So then we'll say, okay, if I take, to prove this then, I'm going to take f of negative x. So that means it's going to be substituted in for all the x's. Right? So I've just taken this and plugged negative x into all the places, right? Everybody's okay? Okay. Now, what do I know about f1, f2, yada, 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 all the way to fn? What can I say about all those functions? What did I assume that was true about them? Each of them is even, right? And I know by the definition of even functions that f of negative x is equal to f of x. So each one of those I can rewrite just as f1 of x, f2 of x, all the way down to f of x, or fn of x. And now because this is the same as this, I know that f of negative x is equal to f of x. So yes, the sum of even functions is even. If I were to try to prove the same thing about odd functions, you think that's going to be true? Yeah, that works as well. The sum of odd functions is also odd. The proof is going to be virtually identical. You just have to also factor a negative sign at the very end. But it'll work the same way. So that's nice. This is a nice fact to know, because what it allows me to do is I can look at a function and oftentimes tell whether it's odd or even or neither before I even start trying to prove it, which makes the ability for me to make sure that my proof is correct a much higher likelihood if I know what the answer is that I'm trying to prove, right? That's nice. So we're going to stop here. So you guys, we're going to add on to the homework set, 13 through 22. Seeing as we don't meet again this week before the homework set is due, this assignment is going to go on to next Sunday's homework check. So I'll always try to give you at least one day in class where you have a chance to ask questions about the homework before I expect it completed. So you really have 10 days before this assignment is going to be due. Obviously, don't wait 10 days to do it, but I want to make sure that I give you guys an opportunity to be able to ask a question about it beforehand, before it's due. And that should be reflected on my Notre Dame. I've made a separate assignment for the next homework check already and have started by adding this assignment to it. Any questions